Merlin. Uh, so the problem Merlin solves, I think that the acronym that goes into the name Merlin involves machine learning. Um, but you don't have to be doing machine learning to use Merlin. It is a workflow manager just the same, able to run any other number of things. So the Maestro coordinator that we were just working at is a single process. You set it running, it reads the YAML, it's gonna, unless you run it in the background, it's gonna block and wait for its tasks to finish and it to notice that it finished the tasks and move through its directed graph until it finishes what it's working on or some other conclusion. If your pipeline is very, very large, if you have steps that have lots and lots of concurrent tasks, then that single process as the coordinator is going to end up being a bottleneck, preventing the issuing of new tasks at a fast enough rate or other slowdowns of that kind. So what Merlin is adding, there's an extra layer between sort of the main interface piece that you run yourself and the actual tasks being run that is populated by some number of worker processes that are actually coordinating subsets of the tasks that have been assigned to them. And the glue that is holding all this together is a message broker or a queue or something like that. So another service process acts as a repository of knowledge. All the tasks get put in there by the primary Merlin process. And then the workers run, they go to the queue, they look for tasks that are available to be worked on. They pull them out of the queue, they start working on them, and then they let the queue know if that was finished or not. And then the main process at the very beginning takes a look at the queue, looks at what's finished, waits to see until all the tasks have been consumed by workers, and then reports back like, okay, your pipeline's done. Yeah. Enter queue, independent workers, pull and execute. If a worker fails, if a task fails, if something goes wrong at that portion of things, the task stays in the queue and can be picked up by a different worker. So there is recovery from failure kind of built into the architecture with this layout. So this is another Lawrence Livermore tool. And I am sure that there is a large amount of overlap as far as like the actual people and developers involved in creating both Maestro and Merlin, to the point that Merlin is effectively an extension to the capabilities of Maestro. Like you've got more block types and more tools that use the YAML. But one of the interesting advantages, if you think Merlin is going to be the tool that you eventually use, is you can start your project in Maestro and then easily, once you get to that point in scalar development, convert it to a Merlin project and not need to redo a lot of that earlier work. So there's a nice sort of on-ramp from the more accessible but lower scale to the higher scale option here. And with the use of those workers accessing a message queue containing the tasks, then you can have many, many, many more tasks in flight on the system at a given time. All right, so Merlin Run is that main coordinator that you as the human are interacting with to kick things off. This is gonna read your YAML. We've got yet another tool using yet another markup language. You're generating tasks with similar format to Maestro, but these tasks, instead of being launched by the coordinator directly or sent to Slurm, are going to be sent to the whatever message queue service you have running to support this. Once that's prepared and your message queue is populated with your pipeline, then you run the workers. Those workers read their own YAML configurations, then they know where the message queue is, connect to it, pull out tasks, and execute them. They're all separate processes. They can run in different jobs, they can be on different systems, different parts of the system, and they can also run at different times. So you're not constrained to a single process staying alive for the entire duration of your job now, in parentheses, except for the message queue. So that message queue is the glue that is connecting all of the pieces together and letting them communicate with each other. The examples are set up so that you'll run a Redis server on the compute node that you're going to use to run the example. For very short things like the examples, just running a Redis queue server in your allocation, super fine, completely acceptable. In production, if you're gonna want this thing to be able to live a long time to support a long campaign with many jobs and lots of tasks, this is also the kind of thing that you want to end up running in Spin instead of running on Perlmutter itself. But the workers themselves and the coordinator, they don't need to stay alive. They can crash, they can OM, they can be on a machine that gets rebooted, whatever can happen to them, and you can just replace them and things will be okay as long as your message queue is persistent. And what actually is Redis? That is in-memory key value store. So our actual configuration in the files in the examples, we're going to mark that as localhost. So because it's going to be running on the same allocation as all the workers and the coordinator and the actual tasks. If you're running in Spin, you're going to change localhost to whatever address is network connected to that. There is at least some support for recovery of failures in Redis. You can do checkpoints and restarts, but if you're doing a checkpoint, then you're going to lose everything after the checkpoint. And that, for these purposes, you might still end up with a corrupted workflow state. There's a little bit of sort of logging and like record rollback replay kind of functionality, but Redis isn't really designed for super durable persistence in the way that like Postgres is. So you still have a little bit of risk surface on the making sure that you can actually keep your Redis process alive consistently over the duration of your campaign. Another animation failure. Okay, so if you're scaling up to thousands or millions of tasks, that's when you want to upgrade to Merlin. If your campaign is longer than the duration of Slurm jobs, then that's a good reason to upgrade to Merlin. You're getting automated retries, so if you've got things that are flaky and fail, this will help you out. And Merlin it's got a dynamic arrangement of the graph structure of tasks, not a static one built in advance. So you have some more flexibility over how your pipeline progresses as it's running. Oh, and multi-node. If you don't need to scale up to this big size, you might want to stay with Maestro. If you don't want to worry about operating your Redis, okay. Although a Maestro operator still needs to stay alive for the entire duration of your campaign, which would be the same restriction as a Redis for keeping your campaign alive. Still, we don't have really deep or powerful tracking of history provenance yet. All right, so what are we adding to the infrastructure relative to Maestro, and what are we adding to the YAML? You have to run the Redis server. And you want to run it with this daemonize option, and then that'll be on your compute node as you're going. Again, I'll remind, I suggest avoiding running Redis on a login node. You might have a port conflict with someone else doing the training, or you might forget about it and leave the process running, and then it's going to sit there and use a little bit of resources until the login node gets rebooted at some point in the future. You can check that your server is running by using this Redis CLI ping command. And then on to differences in the YAML. That needs to configure your communication with the broker, with the Redis, and with your results. So there is this broker field in the YAML, and you tell it you're using Redis and where it is running and what port to connect. And then you want your results backend to use the same Redis. This encryption key part takes care of itself. And then you can use this Merlin info. It'll go in, it'll parse your YAMLs, and it'll check that, do all of the support pieces and configuration in here actually meet sufficient requirements for running. When you're actually running the Merlin commands, you have to do them from the directory that has this configuration, so it knows where to actually go find the Redis broker and so on and so forth. All right, so the details of the YAML in specifying your workflow itself. A lot of the pieces are the same as Maestro. Description, environment, batch, the global parameters, the study. We add a few more. Merlin resources workers. Those are the worker pools that are taking work out of the Redis and running them wherever they see fit. They themselves might be submitting Slurm work, or they themselves might be finding pieces of work that don't have resources defined and running them locally wherever you ran the workers. Merlin samples parameter generation from scripts. So now you have the ability to feed in some Python so that you can have more power in actually preparing your inputs, your arrangements, your requirements, your tokens, and so forth. This task queue field is sort of the identifier that actually goes into your Redis and links to records in there. And you've also got a YAML for your worker configs. So you'll have a concurrency, how many workers am I launching at a time, how many tasks am I running at a time. So taking all of that together, the life cycle for running in Merlin, you start with Merlin run with your Redis already running, and that is going to read your pipeline YAML files and insert them as tasks into Redis. Then you're going to launch Merlin run workers. You might do that in the same location that you just did Merlin run. You might do that in a compute allocation because you want your Merlin runners to have access to a local host that can run some small compute. You may do the workers on the login node. There's choices there. When those are set up, they're going to start accessing the Redis queue, pulling out tasks, and running them. And they're going to keep doing that until all of the tasks have been pulled out of the Redis queue and it's complete. All right, on to the first example. So we're going to generate. That's going to be done locally. We're going to process 5 different tasks, and then we're going to aggregate. And so we're going to pull the results of those 5 different processing tasks into one thing. So this task queue simulations is going to be the Redis ID for holding the tasks that are in that middle step. And we're going to use the wildcard dependency that Maestro introduced as the prerequisite for aggregate to run. So it's going to wait for all 5 processes to finish. You start with Merlin run. That's going to place the tasks in the Redis queue. We've got workers with concurrency 4. So this is intentionally less than 5 to see the blocking and waiting until workers free up to do the last task. And in the output, you'll be able to see that gap in the status information. Another side thing that you can do during this example, if you want, you can Control C the Merlin run. Or you can Control C the workers run before it finishes. And you can see how it will recover from that work being unfinished when you restart a new set of workers, and they'll pick up back with any unfinished tasks, which depending on whether you Control C it when 4 are running or 1 running, you'll see different status outcome. The example is configured to put the outputs of these runs onto Scratch. So you go to pscratch and there'll be this process param.1 files, and the results.txt will be in there. All right, so if we did something like this in Maestro, we would get 5 Slurm jobs, and then the Maestro process would sit there and check for Slurm job completion from the queue. And then once those are done, it would run the last aggregate step and return. Here, Merlin is moving those 5 tasks into the Redis queue, and the workers are running them directly. We're not doing the Slurm step with this example. So those are all running on local, which would hopefully be in an salloc that you have your Redis server running. So Maestro, if you lose the Maestro process, if you Control C before it finishes, it's going to forget everything about your workflow state, and it's going to rerun your prerequisites even if things were completed. Merlin is going to still have access to the Redis queue, and it's going to see what tasks had finished and what happened, and it's going to be able to pick up in the middle and use some of that already completed work. The Maestro coordinator has to run the entire time. Merlin, the different pieces don't have to be running the entire time, except for Redis. All right, automatic retry. If you're running on HPC at scale, then some tasks are going to fail. There's IO errors, DVS does stuff sometimes, Luster does stuff sometimes. You can out of memory, node fails happen. The bigger your job, the more likely that's going to bite you. Merlin retry is the token that gives you access to the exit code from a task. If you get something non-zero, then that task is going to be reinserted into the Redis queue. There's a retry delay parameter that you can set. You can have it wait 5 seconds or 10 seconds or whatever you want before a new worker can grab that task. And you can limit the number of retries so you don't get stuck in an infinite loop rerunning a task that's going to fail every time because it's somehow otherwise faulty. Once you've got this set up, as a human, you don't have to intervene in any of the retrying stuff. It's going to do what it can, and then at the very end, either you're going to have the work that you want, or you're going to have logging that indicates that, oh, we reached max retries, and that was the failure. Different workers can pick up work that were dropped by other workers. So say you've got your workers spread off over a couple nodes and one of them fails, the ones that are left running are gonna be able to cover the slack. Resume failed, you're gonna have to have preserved the log and kept the task list unchanged. So you have to make sure that when you ran GNU parallel, you did these setup requirements. And you're gonna need to put in a new batch job or do a retry of some other sort if you're trying to resume failures using GNU parallel. So Merlin restart is a token that gives you access to partial recovery of a task. If your task has some kind of functionality that lets it preserve partial work inside itself, then you might have an exit code that can trigger a restart section. So if you've got checkpointing set up inside your task, or some kind of error recovery that sends a signal through the exit signal. Maybe it's going to do this before a particularly flaky task that you know is upcoming. The restart token can catch that exit code, recognize it, and then act based upon what's the YAML has defined in the restart section. And so the restart section might include things like, okay, well, your checkpoint is placed in this location. This is the command you use to resume it. This is how you define restarting from a checkpoint instead of running the task from the very beginning. And that way you can, protect expensive work that may be partially done and checkpointable, but the task itself gets lost at a late phase. You also have the option for a hard fail. So if something completely unrecoverable happens and you know that everything else in your entire pipeline is not going to be useful because of this failure, you can specify that too. So, maybe it discovered that your input data was corrupt at the very beginning. Maybe you misconfigured something and you're actually working with the wrong temperature or the wrong pressure, some other parameter. You can hard fail the entire pipeline that way. Okay. Example 3, a large parameter sweep. So this is the pattern that is going to be something so big that you shouldn't do it in its signac, it's going to be bad for the file system. So your static YAML lists, you could put tens or hundreds of values in there, but thousands or more is going to be a cluttered, ugly YAML file that's not really usable. By using Merlin samples, you can generate parameters based on writing a Python script that acts as a generator. So at the very beginning of starting your campaign, generate your command and spit out this big sequence of whatever the values are that you're going to be putting in. So this is going to maybe make a NumPy array. And you've got column labels that can link into the NumPy array. And then each row in that array is going to be one task, kind of shaped like GNU parallel and its flat files. But you can easily now have thousands or more rows, uniquely specifying tasks. And then you've got this token that allows you to path to a directory that stores the metadata relating to those samples. Okay. Now in the example, we've got concurrency 32, so each worker is being allowed to run 32 of these generated tasks, 1,000, so 31 batches per worker. You can put in more workers to go faster. You could maybe put in more concurrency, but then you might be limited to the amount of cores available on whatever you're running the workers. All of these workers are still talking to the same Redis queue. That's how they're distributing and balancing work between themselves. You can scale horizontally. You can have multiple job allocations and run workers in each one of them. They'll all talk to the same Redis queue and coordinate. If those jobs end for some reason, the time runs out, the tasks are still in Redis, it's persistent, you can start new jobs with new workers and keep going. And that's how we're able to have commands that can do work productively over the course of campaigns that are longer than 2 days or what fits in a single Slurm job allocation. All right, unlike Signac, there are 3 levels of directory hierarchy on the file system storing the data related to these tasks. So you no longer have that more than thousands of directories in a single directory degrading the file system metadata performance. Large flat directories, bad. So in the progression of tools, we're getting close to the end. We've accumulated a lot of different capabilities into Merlin. We've got more than single node parallelism available now. We've got a lot of power for defining parameter spaces and very large ones. We've still got the ability to define graphs, dependencies, pipelines, workflows. And we're doing it with YAML files. We're also able to now do it with generators and programmatically. And we've got this persistent message broker that is keeping the state of your workflow alive into the long time duration, longer than the span of days. And the fault tolerance is good. The scale is good because we've got lots of workers able to work in parallel at the same time on different resources in different places. We still don't have that history, the exact records of which files went into which other things. This information does technically exist in the Merlin data. Like your intermediate files are there if you're not cleaning them up, if you don't have to worry about like extra storage of keeping them. Your commands can be reconstructed as long as you have all that thing, but it doesn't really have the infrastructure, the tooling, the command line pieces to make that easy. You would be doing some digging and engineering and pipe tinkering, plumbing to actually get that out. Yeah, and it's a continuation of Maestro. If your project started in Maestro and then you realize that you need to get bigger, you could have moved into Merlin and only needed to worry about those extra few kinds of blocks and definitions. Vocabulary review. All right, so the message broker. This is the glue piece that is holding all of Merlin together. Your coordinator to your task repository inside the Redis queue, to your workers, to where the work is actually being run. The task queue lives in Redis. That's the state of your workflow, what is finished, what is done, what is errored. That's where it lives. The worker, those are the processes that are taking work out of Redis, running it, and then letting Redis know that, oh, I finished, oh, I failed. Concurrency, that's how much you let each worker do at the same time. Retry, that's one of these token entry points for getting information about the outcome of running different tasks. Restart another. And Merlin samples is the programmatic entry into writing generation scripts for building large and complicated parameter sweep kinds of task definitions. App.yaml, that is the configuration file for setting up the Merlin infrastructure. That's not where you're specifying your workflow, it's where you're putting your Redis location and your port and your task queue names and all of those pieces that keep your workers and your queue and your coordinator working together.